Another parameter is about the height of gas pressure. So, increase in the top pressure of the blast furnace reduces the gas linear velocity, which can be seen from the Argand equation. If you look at our previous lectures where we talked about the aerodynamics of the blast furnace, you can see from that gas if you increase the top pressure of then the gas linear velocity will decrease, and so this facilitates to increase the blast volume. So, to maintain the same gas linear velocity as in the conventional way, what one has to do? One has to increase the blast volume. So, in one way and that is the one of the requirement to increase the productivity. So, that is a Q factor. So, blast volume is can be, so you have a height of pressure, then blast volume, more blast volume can be put into the blast furnace. So, low gas velocity facilitate better heat and mass transfer. Now, another advantage, if the gas velocity is low, the residence time of the velocity is higher in the blast furnace, which means when residence time is higher, so it has more chance to react. So, mass transfer would be better. Similarly, it has more chance to give up the heat to the charge. So, heat transfer is also better. So, low gas velocity facilitates better heat and mass transfer. So, all these parameters contribute towards increasing the productivity, that is to one more carbon. So, next figure shows the effect of top pressure on coke burden per meter cube of furnace volume per day. So, you can see that as the top pressure increases, these are really high capacity furnace which are being used nowadays. This is somewhere in 80s or like that. So, quite old, but this is the one which are being used nowadays. So, one can see the, and most of these modern furnace now they are equipped with the high top pressure somewhere 2 to 3 kg per centimeter square of that range. So, one can see certainly that coke rate has increased with the increase of the top pressure. So, that is going to increase the productivity of the furnace, and this figure gives a typical gas pressure profile in the furnace. So, you can see that pressure drop in this region is very high. This is between sort of a dripping zone and the upper one can say about the cohesive zone, and if you take the upper boundary of the cohesive zone at which it starts softening the charge, and from there we take, so it is again almost same. So, this is a quite high pressure drop in comparison to in the Stoke region. See, Stoke region height is very high. So, there is and that is why also the gradient of this pressure drop is quite low. Here height is low, but still the pressure drop is very high. So, very high pressure drop exists in the lower part of the blast furnace, and across the cohesive zone, in fact the height is very low, pressure drop is quite high. You can see that pressure drop is quite high, and which is also indicated by this pressure gradient, very high gradient, 1 order magnitude almost. So, this is the importance of the cohesive zone or cohesive region, because this is the one which offered maximum resistance to the flow, and that is why lots of charge preparation is needed to control that and to narrow it down. So, this can be reduced, and if you look at the normal gas pressure from the injection point. So, this is at fuel level about 2.5 or close to 3, and you can see just within almost 12 meter or so first 12 meter the pressure drop goes almost a drop to 50%, and remaining almost 14-15 meter it just drop about 0.2 bar, hardly 10%. So, it is a big drop in that region, 50%, and after that it is very little pressure drop, about 10% or so in the upper part of the furnace. So, this lower part of the furnace is very critical and has to be maintained to have a good productivity of the blast furnace. This is the one which dictate all qualities of the raw material and even the blowing of the air and other thing. It dictates, it controls, and thus it controls the productivity of the blast furnace. So, there are some of the limiting factors in the productivity. So, as mentioned before, there is a counter current reactor blast furnace, solid gas reactor, which determines its efficiency and productivity. So, some important limiting factors are fluidization of bed in the dry zone, loading and flooding of slag in coke bed, decrease in bed voidage due to softening and swelling. So, all these factors have been discussed in details in previous lectures. So, limit of productivity caused by fluidization is shown in the next slide and summarized in the table. So, again I will emphasize about this fluidization, loading, flooding and decrease in voidage. So, with respect to that, because the slag and liquid is flowing down, voidage is reducing, and so that will carry away more liquid and it can deteriorate if this is not maintained. Velocity is high, more fluidization, because you have a smaller particle size here also. So, fluidization may occur localized one. So, this is the thing which actually it is talking about. So, this gives one idea that the limit of productivity caused by fluidization at the blast furnace top and the effect of high top pressure. So, if you have a see, this figure is quite complex and it is a very good figure to judge what sort of productivity one can have it. So, furnace output at some 550 coke rate. So, that is a blast volume also is there, and at what height of top pressure you are operating, you can choose one of those lines and then you can decide based on that what sort of particle size you should have in the blast furnace to achieve that sort of furnace output, depending of course on the gas density. So, gas density curve is here for the 0, and this is actually the your material, charged material density or ore density. So, 5 gram per centimeter cube. So, depending on that one can actually, and these are showing the top pressure high in the furnace. So, these are all the top pressure in the furnace. This is the gas density, these are the ore density. So, based on your top gas pressure, which one you are choosing, accordingly you can take the graph of that one, and accordingly also you can plot the line and similarly for the gas density and charge density, you can select the graph at a particular top height of pressure, and based on that you can select what sort of size it should have. So, this really showing sort of probably the minimum size, and this because the gas density is also important with respect to that fluidization should not occur. So, that shows that sort what sort of size is needed to so that fluidization should not occur. So, based on that one can calculate a size distribution, also about the charge depending on the on all these parameters, gas density, charge density, the height of pressure, the Koch rate and the blast volume. So, these are typical values which are shown, and one can really get the fair idea about various parameter from this graph. So, it is a very useful graph for the from productivity viewpoint and selecting approximate parameter for the optimum productivity. So, this figure shows also dependence of productivity per meter square earth area per 24 hours on particle size of ore of density 5 gram per centimeter cube and height of pressure. So, fluidization is the thought to be limiting. Koch rate is 500 kg per ton of hot metal, and Koch has 87.5% carbon. So, when a height of pressure is 0, so it is the same as atmospheric, then the minimum ore size which is required is 6 millimeter without fluidization. So, and that is how this is calculated. Below that one fluidization will occur. So, you can't have it. So, it should be sort of a that range. So, mostly as we said 10 plus millimeter size is a good one, and so highest production rate 50, but if you have your ore size 8 millimeters, you see your productivity is increased, which of course you can even go in a reverse way and you can check it, and you can see your furnace output will increase. And if your height of pressure is 3 and minimum ore size 6, you can say see the productivity is almost 95 ton hot metal per meter square per day. And when the minimum ore size is 8 millimeter, it further increases the productivity. So, this gives you an idea that one thing is about the height of pressure, how it is beneficial in increasing the production. So, for the same one from 50 to 95, almost double it has become, and one can also from this figure choose the appropriate parameter for the higher production. So, maximum productivity can be obtained if size of coke is kept between 3 to 5 times of ore size. So, usually sinters can do that thing, and many of the modern blast furnaces they operate almost 80, 90 or sometimes even 100% sinter or pellet. Slag bulk and viscosity is low, all less than 10 millimeter size are screened, sinters should be superfluxed, so less slag volume. Coke and ferrous charge should be in the superflux also it's actually reduce this cohesive zone and melting temperature delayed, so it's increased. So, that is one good thing. Coke and ferrous charge should be resistant to breakage, use of high top pressure, control of alkali metal and controlling the channeling etc. These are the factors which by controlling that you can achieve the maximum productivity in the blast furnace. So, there is one example based on this which we will take now. So, you can understand how you can calculate also the productivity beside of course having a this diagram or figure which give the approximate idea. So, carbon burning capacity at the TUR of a blast furnace is reported to be 20 tons per square meter of active hearth area. TUR's project or 2 years projection actually in 0.2 meter inside the hearth and depth of penetration of 12 millimeter diameter hearth is estimated to be 2.5 meter. So, this is actually depth of penetration means the raceway depth in a 12 meter diameter hearth is about 2.5 meter. Useful volume of the blast furnace can be assumed to be 25 times of the hearth area meter square. If the coke rate of blast furnace is 750 kg per ton of hot metal, coke contains 70% carbon and 75% of coke burns at the TUR. Determine the productivity in tons per day per meter cube. So, now here you have to calculate the productivity of the furnace. Most of the parameters are given. So, what we have to do, we know the diameter of the hearth 12 meter, TUR protrusion inside the hearth is 0.2 meter. So, that is not acting as the active area. So, we have to decrease remove that. So, depth of penetration raceway is about 2.5 meter as we mentioned. So, that is quite active area what we say. So, the effective hearth area would be is 12 meter minus 0.4. So, 0.2 meter each side of the TUR protrusion. So, it will become 0.4. So, 12 minus 0.4 and then minus. So, if we take a 12 minus 0.4 essentially is 11.6. So, 11.6 now we know the raceway is 2.5. So, that is also extending. So, both the sides. So, into 2 5. So, 5 meter. So, this minus this is going to give us the effective hearth area. So, that this is being used for the raceway, this is inactive by the TUR protrusion. So, what is remaining would be the effective hearth area. So, when we calculate this effective hearth area, it comes from the 71.5 meter square. So, given that the carbon burning capacity at the TUR equal to 20 ton per meter square of effective hearth area and that coke contains 70% carbon. So, really coke contains 70% carbon, which means we can calculate the coke burning capacity from this 20 tons and 70%. So, it gives about 28.57 tons per meter square. So, effectively coke burning capacity is about this much 28.6 tons per meter square. And now we have to find out the coke rate actually. So, now 75% of coke burns at the TUL level, which is given again. So, the actual coke burning capacity, so total burning what we got the burning capacity of this was 75% only it burns. So, actual coke burning capacity is 21.4 tons per meter square. So, coke consumption, actual coke burning capacity into effective hearth area. So, actual one we have calculated this, and the effective hearth area we have already calculated 71.5. So, we multiply this one, that is going to give you 1531.5 tons per day. So, this is the coke consumption which is required, and coke rate is given 750 kg. The coke rate of blast furnace 750 kg per ton of hot metal. So, but 75 so it is a 0.75 tons per ton of hot metal. So, coke rate we have, coke consumption actual we have, then we can get the productivity by P by Q by K. If you look at our the first definition of the productivity, which says Q is the coke burned in tons per day and coke consumed in tons per ton of hot metal. So, coke burned we calculated and consumed, that is coke rate per ton of hot metals. So, that is really bring us to this. You divide, so the productivity of the blast furnace is 2042 per ton of hot metal, but what is determine the productivity in tons per day per meter cube. So, this is in ton hot metal per day. So, useful volume, now this actually with the volume if we divide it we can get that one. So, useful volume is mentioned 25 times of total hearth area. So, total hearth area is, so you can see this is given here. Useful volume of the blast furnace can be assumed to be 25 times of the hearth area in meter square. Okay. So, this is actually, so that should be meter cube. Because it is a volume. So, productivity would be this 2042 divided by the useful volume, that is going to give you 0.722 ton of hot metals per day per meter cube. So, this is the productivity in ton hot metal per day per meter cube. So, this gives you or this example tells you at least how you can calculate the productivity of the furnace, and that would be useful to know.